All right, welcome. Today we are going to crack the code on one of the slickest, most powerful algorithms out there. We're going to see how computers can search through just insane amounts of data at speeds that honestly feel like magic. Okay, let's jump right in. So, to really get a feel for what we're talking about, let me throw a question at you. Imagine you have a list of 1 billion names, all sorted perfectly. You just need to find one specific name in there. How long do you think that would take a computer? A few hours? Maybe a whole day? Just take a guess. Well, if you did it the simple way, what we call a linear search, checking name number 1, then number 2, then number 3, it could take you up to 11 and a half days. But with the algorithm we're looking at today, binary search, it takes a grand total of 30 steps. That's about 30 milliseconds. Not days, not minutes, not even a full second. Milliseconds. So, how on earth is that even possible? So how do you go that fast? Well, here's the best part. The core idea behind this incredible speed is something you already do, probably without even thinking about it. Let's call it the dictionary trick. Seriously, just think about the last time you looked up a word in a big, heavy dictionary. You didn't start at page 1 to find the word synergy, did you? Of course not. You used a much, much smarter system. You just instinctively crack it open somewhere in the middle. You glance at the page, see you're in the M's, and realize your S word has to be in the second half. And just like that, poof, you've just thrown away half the dictionary. You just do that again, you take the remaining half, split it in the middle, and keep doing that until you land right on the word. And this isn't just for old school books. Think about finding one specific moment in a long video, like security footage. You don't watch it from the start. You jump to the middle of the timeline, see if your event happened before or after that point, and then jump to the middle of that relevant section. You're doing a binary search on time. So let's give this trick its proper name. This is binary search. It is a super efficient algorithm for finding something in and this is the most important part, a sorted list. It works by repeatedly chopping the search area in half. And that word sorted is everything. It's the secret sauce that makes the whole thing work. Okay, so we've got the real-world idea down. For section 2, let's dive into how a computer actually thinks when it's using this amazing divide and conquer strategy. Let me just hammer this point home one more time. Binary search only works on data that is sorted. If your list of numbers or names is all jumbled up, there's no way to know which half to throw away. It's like trying the dictionary trick with pages that have been shuffled randomly. It's impossible. You'd have to go back to checking every single one. All right, let's walk through a quick example together. Our mission? Find the number 8 in this sorted list of numbers. The first thing the algorithm does is look at the dead center. In this case, with 7 numbers, the middle one is easy to spot. It's the number 7. Now comes the decision. Is 7 our target? Nope. Is it smaller than our target, 8? Yes, it is. And because we know the list is sorted, we know for an absolute fact that our number 8 cannot possibly be anywhere to the left of 7. So, we can just completely ignore that entire first half. Think about that. One comparison and we just cut our problem in half. So our world just got a lot smaller. We're now only looking at these 3 numbers. And what do? The exact same thing again. We find the middle of our new tiny list. In this case, that's the number 10. This rinse and repeat strategy is the heart and soul of this algorithm. All right, time for section 3. Let's get a little more technical and look at how the computer actually keeps track of everything. It doesn't actually delete parts of the list. It uses these handy little markers called pointers. So instead of making new, smaller lists over and over, the computer just uses 3 variables. Think of them as bookmarks. Low marks the beginning of the section we're searching, and high marks the end. At the very start, that's, the whole list. So, from our low and high bookmarks, we figure out the middle, mid, which points to the number 7. Then the computer asks itself that one crucial question. Is this middle value less than, greater than, or equal to the number we're looking for? And we know the answer to that one. 7 is less than 8. So all we have to do is move our low bookmark. We just slide it over to the spot right after the middle. Boom. The entire left half is now officially out of bounds. Our search area just shrank without us having to copy or delete anything. And we just run the same play again. We take our new low and high positions and recalculate the middle. The new middle of our current search space is now pointing at the number 10. We ask the question again, is 10 bigger or smaller than 8? It's bigger. So this time, we know our answer can't be to the right. We move the other bookmark, the high one, down. And would you look at that? Our low and high bookmarks have squeezed together and are now pointing at the exact same spot. We've trapped our target. We found the 8. Okay, on to our final section. Now the logic here seems pretty simple, right? But actually writing the code for this perfectly is surprisingly difficult. Let's talk about what separates beginner code from professional, rock-solid software. You might think this is a piece of cake to code up, but history shows that even the experts get this wrong. Get this, John Bentley, a legendary programmer, once wrote that he assigned this as a problem in a course for professional programmers, and 90% of them got it wrong. He even admitted that his own first published version of the code had a bug that nobody found for 20 years. So what was this super subtle bug that fooled so many smart people? It all came down to this one innocent-looking line of code. The intuitive way to find the middle is just low plus high divided by 2. But that formula is a ticking time bomb. The safe, robust way to write it is low plus high minus low divided by 2. Here's the problem. If you're dealing with a gigantic list, like billions of items, your low and high numbers can be huge. And if you add 2 huge numbers together, the result might be bigger than the maximum number your computer can store in a standard integer. It's called an integer overflow. Think of it like a car's odometer rolling over from 999,999 back to 0. It can cause the calculation to produce a crazy, unexpected result, often crashing the whole program. The safer formula cleverly avoids that huge addition.
So, why do we care so much about this? Because this divide and conquer idea is literally everywhere. Its ridiculous speed, which we call O log n, is what takes you from an 11-day search down to 30 milliseconds. What O log n really means is that even if you double the size of your data, it only takes one extra step to find what you're looking for. It's wildly efficient, it uses practically no extra memory, and it's the engine behind searching your phone's contacts, finding products online, and even pinpointing bugs in code.
So we've seen how a simple trick for finding a word in a dictionary is actually a cornerstone of modern computer science, one that's so subtle it even has its own famous bug. I'll leave you with this question. Now that you know the pattern, this idea of cutting a problem in half over and over, where else do you see it hiding in your digital life? You'll probably be surprised how often it's working for you, right under the surface.